chat. I think we're good there, and I don't see any hands raised. So I think we're going to move on to David Firshein, Brouillon Energy. He's doing some interesting stuff, very passionate, so passionate that he talked to me for months, and I'm an investor in full disclosure. But Tiff, thank you very much. And I know it's a little bit of a tough time for you right now, so we do appreciate you joining us, and our sympathies to your family. You're mute right now. But
thank you so much. I'm putting in here a link for people to try the carbon pricing tool for free for 2 weeks. There's no obligation, but it's kind of fun. Thanks so much for hosting us.
Cool. Thank you. And David, you're still with us, right?
Yes.
Oh, there you are. I'm sorry. You're right there. My mistake. It's been 20 hours we've been going, so I'm a little tired at this point. But anyways, David, I'm going to let you take it over, and hopefully you won't need me for the first minute or two, because I'm actually going to hit the restroom. But thank you so much for being here, both of you. And David, the floor is yours.
Awesome, Matt. Thank you so much. And thanks for the invitation. Hi, everybody. Good to be with you. My name is David Firshein, and I'm the Chief Financial Officer of Renewable Energy Corp in Berkeley, California. And I'm just going to go ahead and share screen and pull up our simple deck. And actually, let me pull this to the right. 1 second. So Berluin's a very unusual company, which has been in a very long development stage process, a seed stage process, which makes an extremely advanced electric heating element. Now, it tends to get confused with what is popularly called cold fusion. And some people still say it is cold fusion. We believe that what we're doing is a controlled electron capture reaction. And I'm going to get into that here in just a minute. But we obviously are going hard at the whole problem of pollution emissions that are generated when human beings, civilization makes energy. So everybody knows that. And everybody knows what the problems are. There's so many coming out of current energy generation. Our solution, and we're still rebranding this, we just recently begun to make a change, but it still says micro nuclear energy with zero hazardous waste byproducts. When we say nuclear, what we really mean is nuclear energy density level thermal energy generation, heat generation. And what we make is something called a hydrogen hot tube. And down here on the right, you see the actual device. Here's our CAD drawing to the left. What we really make is a long, thin metal tube that gets hot. And what's inside of the tube, which is very uniquely constructed with advanced material science solutions, is a very small amount of ordinary hydrogen gas, not deuterium, nothing fancy, just hydrogen gas. And we apply the input of electricity pulses to the hydrogen, which is sealed in that metal tube, on an extremely rapid, very high blast, very, very short pulse parameter. We are blasting there's actually a metallic catalyst rod inside of that tube. You can see the end of it sticking up at the top and the bottom. It's about a 1/4 inch in diameter. And in this actual photo, it is only 18 or 19 inches long. But at commercial lengths, initially, we expect it to be 2 to 3 feet long. And so that tube within a tube, that metal catalyst rod, which is technically has a very small hollow space in the middle of it, so it's really a tube within a tube, has hydrogen gas that's in there, which is sealed and pressurized. And we blast that catalyst rod with this electronic gizmo that we've invented here called a Q-pulse generator. We're literally blasting 15 kilowatts of electricity into that catalyst rod between several 100,000 times and several million times per second, depending on what we choose to do. And that excites the hydrogen atoms at the atomic level inside that tube and generates heat. And it does not generate any other hazardous waste. There's no carbon emissions coming out of that tube. There's no penetrating radiation coming out of that tube. We've got 12 years of monitored, measured data that prove this over and over again. All that comes out of this tube is heat and barely a trace of inert, harmless helium, which is very hard to measure at a small level. You actually have to run it at a much larger commercialized level to even be able to detect it. But we have been able to detect other byproducts that say that the energy density coming out of this is at a nuclear level. But it's not traditional nuclear because there's no hazardous waste. So people, of course, immediately jump up and say, well, that's impossible. You can't do that. But you can come see it running in our lab. And in fact, we're going to see it at the end of this presentation. That's a very quick description in layman's terms. Again, I'm the chief financial officer, not the engineers running this team. And so here's part of the point. You know, you can get, and this is simplified just to get the point across. Hydrogen is obviously incredibly abundant, and especially if you're just looking for ordinary hydrogen gas, and you only need to use an incredibly small amount of it. Imagine that this 8-ounce bottle of water, the H2O in here, that you could take the hydrogen in this volume of water and use it as the fuel for the thermal generation that this device is creating. Well, if you take that amount of hydrogen and you out of this volume of water and you put it in an internal combustion engine of some kind and you burn it in a chemical reaction, you're going to get the same energy density in terms of order of magnitude, roughly as gasoline. However, if you could react it at the atomic level, effectively at the nuclear level, without causing hazardous waste byproducts, you will get up to, in this case, 355,000 times more thermal output units in terms of measurement than you would just burning it. So at a nuclear level, obviously tremendously dense, you can actually get up to 1,000,000 times more in terms of leverage. And that's the whole point in very simple terms. And here's some of the key features and the results. What does this really mean? Well, if you take this, let's just call it, because it's only 3/8 of an inch in diameter. Here's a letter opener. This is about 3/8 of an inch, okay? And that's how thick it is on the outside. So if you're putting electricity into this and you're generating more thermal watts of heat out than electricity in, obviously the bigger that ratio gets, the more commercially valuable this becomes. So especially if it's not making any pollution. And obviously if it's patented and it's controllable and it's safe. In this particular case, it's so safe as far as we're concerned. This is actually safer than natural gas being delivered to a home or a commercial facility. And that's actually very provable. And so the ultimate goal here is heat on demand. And what's amazing about our device is it's completely controllable. It works every time. It works currently at a lab scale level, not a commercial level. But what we've been able to do, this next graph is actually shows you about how we can pack it together and build to any size demand. But here's an example of just a very few of the results we've been able to produce. The blue line on this graph is the amount of electrical power in watts. The heat out is the mauve green line, which is obviously, over 2 times higher and even up to close to 3 times higher. And then the coefficient of performance, or COP, is the heat, the power out, the thermal energy out, the heat out, divided by the electricity in. And that gives you your ratio. The higher we can drive this ratio, the more significant and valuable this becomes. Now, we've done this in our devices, in our lab in Berkeley, California, over 1,000 times. And it actually works. And we have continued to expand its capability and its demonstrability to the point where we now have it running steady state. It's run, to a small degree steady state, then a little bit more, then a little bit more. We also run it in sine waves. We do a lot of things with it. And we spend our time engineering the improvement for demonstration purposes to reach the point that we are at today, which is we're actually now beginning to proceed with the commercial scaling of this process. Why? Because we've actually proved at the scientific level that it works. A lot of people still don't agree with us, but slowly more and more people are beginning to agree with us. And we envision that as we get each one of these tubes to work, especially coming right off of a production line, and this device was designed and built to go straight into manufacturing, that we can pack these together to meet any size demand. Now, obviously here we're only producing, a little over 100 watts. This was actually several years ago. It's a clean graph, so we still use it as an example. We currently today, in the size that we've been able to afford in the footprint, with just an 18 or 19 inch long tube, this catalyst tube, we are generating around 250 to 300 watts out. This right here is actually comparable to what the US National Labs announced back in December. I suspect some of you may recall that Jennifer Granholm and the current Biden administration got up on TV in December and said, we've achieved a fusion reaction for a very brief moment of time, but it was 1.5 times the amount of energy in versus out. Now, what they didn't count was the 99 or 98% of the energy that it took to set up that experiment. They were just talking about the 1.5x COP, which ran for literally a billionth, 1 billionth of a second. More thermal energy out than electric power going into the grain of rice sized fuel pellet in that hot fusion experiment at Lawrence Livermore National Labs. That was 4 months ago. We've been doing this for years. We do it over and over again under control, on demand. It runs for hours, days, weeks. Our best performing catalyst rod ran for 1.5 years, able to repeat this over and over and over again. And so, it's something that we can rely on. So the point is that as we continue to build its efficacy, you can pack it together to meet any size. Our goal is to take this tube up here and scale it up into the kilowatts, where we're talking about getting, 2 kilowatts of thermal energy out for, say, 500 watts in, or ultimately 5 kilowatts of thermal energy out for 500 watts in, 0.5 kilowatt. That's where we're headed. And let me jump to just the bigger business picture of this device. We've already got some commercial traction. We've already generated over $1.5 million of actual commercial revenue based on very early stage license agreement and technical sales. And we've actually sold to a very large defense contractor, well-known company, and we're beginning that relationship. So you could see the funding of our company to date. We've raised over $24 million. A few $1 million of it has been free or other income or actual commercial revenue or just early stage stuff, and the rest has been equity. And we are right now in the process of closing out our Series C round. We have a commitment from a private investor group that's about to actually fund about $6 million. We're in the middle of the closing stage, and we're gearing up to fund the rest of our early commercial manufacturing stage. We've been doing all this in a 2,400 square foot lab. We're about to move to something 12 times that size. We've already scouted it out. We've already got it planned out, and we are growing. We've got a strong team and that we have put together. And this is classic venture capital 101. So we've done it the right way. We've set it up to be something that can really grow and scale. And just going back to what we've already done, we are generating these results here, which are comparable to the national labs and are orders of magnitude greater. But what we actually have gotten it to is net positive power out of the wall. And at net positive, the entire system, we're now putting in 175 to 200 watts and getting around 250 watts out of it on a periodic basis. We still are improving that. It's not nearly robust enough yet, but it's coming along and it's completely engineerable. The principles work. And now I just want to jump to what it actually looks like. I'm going to run this minute and a half video for about half of it. You'll get the point. This is actually running in our lab today. Here it is generating enough heat to power a small demonstration Stirling engine. And here we go.
What you are seeing in this video is a small Stirling engine that represents any of the many uses of heat in a modern society. It is running off of the heat being generated within a Berlin Energy hydrogen hot tube reactor, or HHT. All of the ancillary tubing and wires around the spinning engine are just for measuring energy, or calorimetry. The HHT is actually producing more than enough LENR heat to spin the engine you see here. In simple terms, our HHT technology amplifies the thermal energy and amount of electrical energy could supply without LENR. This is an efficiency improvement that has great economic potential, especially as it is scaled up.
Now that continues, and if you actually sign an NDA and come on over, you can see this, you can meet our team, you can see all this stuff. Obviously looks like a science experiment, very scientific, but we have now reached the stage where we're not just playing with science principles. We've proven the science, and we've got a lot of evidence to back it up. And we are bringing, what you might expect of a development stage company to move to a true product pilot plant scale up stage. We are headed to turning this into commercial products. We expect to be able to start to spit these things out, literally not quite like razor blades, but in the hundreds and then the thousands and then the 10,000s and so on. And we've got a lot of interest, especially as that grows. So with that, I'll say thank you, and hopefully that worked, and open it up for any questions.
Yeah, David. So I'll kick it off unless I see someone else raise their hand here. But so you're talking about going into a bigger facility. You've added some to the team. Can you give a little more specifics in terms of what you need to accomplish to get this commercialized? And the initial use is basically kind of a reduce your hot water heating bill. Is that kind of a fair assessment, a correct description of it?
Certainly the lower COPs, anything from 2x and up, is a revolution for a boiler manufacturer. We already have a low-level letter of intent from one of the best known, just basic hot water boiler and hydronic heater manufacturers, big, Fortune 500 company that sells stuff at Home Depot. And, initially we're aiming to get the commercial scale COP up into the low kilowatts, even at a few X COP. Anything from 2X and above is a commercial revolution. We'll have to see what the CapEx cost of the device is. It's nowhere near a commercial enough cost yet, but this next stage will get it down into the viable range. Ultimately, our goal is to scale it up to at least 10X COP, where the generation of electricity can become disruptive to a growing degree, not with the intention to be a disruptive company, but to fit in everywhere where this can make a difference, because we're talking about scaling the energy density levels from the ground up. This goes from small to larger over time. So this next stage is going to scale the COP and the actual commercial size of these products to the point where they can be commercially demonstrated and start to go into their first applications. This technology is a little bit analogous to an Intel inside, powered by Berlin inside. Anything that needs a better heat source can use this. So this is ultimately heading for rebranding as an extremely advanced electric heating element. It's a much better way to use the application of electricity to a microscopic amount of hydrogen gas inside a metal system. And it's just a brilliant way to make heat. And our whole civilization runs on the generation of heat, as I think, after a while, it's kind of obvious to most people.
Cool. So if there's no other questions, I think we'll move on to John. He's John Hohen. He also does electrification, or I'm not saying you're doing electrification, but we're still talking a little bit about electricity. So John, why don't you tell us what you're doing and working on? And David, thank you very much for preparing and spending your time with us. And as David said, they are, closing a raise very soon, and
Actually, Matt,
have some big plans.
Yeah, if I could just close it off by saying, look, if you're an accredited investor, this is a great venture investment to look at. We are about done with the C round. We have a little room left. I think within a week or two, that'll just be gone. But we are going to go to a combination of ways of funding the scale up. The total growth capital we need for this to become a massive unicorn is about $25 million in total. And we've got the first chunk of it hard circled. So and that's enough to get into the facility and set it up for a lot of very interested parties. And we're on our way. So
cool. And I obviously, as being an investor, I wish you the best of luck. With that, it's the type of thing that I look at as potential for a big home run. It's still very risky, as any startup investing, and all the usual disclaimers there, and talk to your advisor. And so anyways, with that being said.